Good morning. My name is Marie Rienzo, and I want to welcome you to the NIH Office of Disease Prevention Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and support the development of better methods. Before we begin, I have some housekeeping items. To submit questions during the webinar, there are two options. First, you may submit questions via WebEx by clicking on the question mark in the WebEx toolbar. Please direct your questions to all panelists. Second, you may participate by Twitter and submit questions using the hashtag NIHMTG. At the conclusion of today's talk, we will open the floor to questions that have been submitted via WebEx and Twitter. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be directed to a website to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, Marie. Today's speaker is Dr. Sherry Powles. Dr. Powles is a statistician at the Centers for Disease Control and Prevention. She obtained her PhD in experimental psychology with a concentration in research design and statistics in 2002. She also got a master's degree in mathematical statistics in 2003, both degrees from the University of Memphis. She joined the Division of HIV/AIDS Prevention at CDC in 2002. After discovering a love for international work, Dr. Powles moved to the Division of Global HIV and Tuberculosis in 2010. In her work in domestic and international HIV/AIDS and tuberculosis, she has designed and analyzed numerous group-randomized trials. She has authored several manuscripts on design and analysis of clustered studies, including group-randomized trials and individually randomized group treatment trials. In fact, she published a paper in 2008 in which she invented the label individually randomized group treatment trials, and it has stuck in the field. It's my great pleasure to welcome Dr. Powles.
Thank you, Dr. Murray, both for that introduction and for inviting me to speak on this topic. It's one that I've been interested in for a number of years. And so I'm going to talk about design and analysis of individually randomized group treatment, or IRGT trials. And just a quick overview of what I'm going to talk about. I'll first define what is an IRGT trial and distinguish it from some other designs that share characteristics with it. I'll talk about intraclass correlation and its implications for design and analysis of IRGT trials, and then talk about sample size and optimal allocation of participants to conditions. Then I'll talk about analytic methods for two types of IRGT trials, the reporting requirements for these trials. I'll present on a couple of reviews of published IRGT trials and some future work that's desperately needed in this area. So first, what is an IRGT trial? These are trials in which individuals are randomly assigned to conditions, and then interventions are delivered to groups. And I want to say a little bit about terminology here. I'm going to refer to the treatment that participants are assigned to as study condition, and then the groups that participants receive their treatment in, so subgroups within conditions, as groups. Some people refer to conditions as treatment arms, and some people refer to treatment conditions as groups, so I just want to be clear about that. Within these treatment groups, there is the potential for correlation among individuals to develop over the course of the intervention, and that happens for a variety of reasons. So one can be therapist or facilitator effects. Some therapists or facilitators are more effective than others. There's also group interaction. The group members interact with each other and may promote better delivery of the intervention that way. And the other, and this is not actually an IRGT trial, but participants where participants select themselves into a group based on their preference for a day or time. So the implications of intraclass correlation in these studies, the variance of test statistics can be larger in an IRGT trial than in a trial in which no correlation between participants is expected due to the additional between group variation. So you have the typical between participant variation, and then an additional component of variance that's due to differences between groups. And so the interclass correlation coefficient, or ICC, is the measure of how much of the variation is attributable to groups. So the percentage of the total variation due to group membership. And like any correlation, this varies between -1 and 1, with those two extremes indicating perfect prediction of the outcome based on group membership. And so next, the variance inflation factor. This is the increase in variance that you would expect due to the correlation within groups. And this is a very important quantity. So it is 1 plus m minus 1 times the ICC, where m is the average number of members per group. So it's really important to notice when looking at this formula that the variance inflation can be impacted both by the ICC and by the number of members per group. So you can have what looks like a fairly small ICC, but if your group sizes are large, it can still result in quite a substantial variance inflation. So what this does is to reduce the sample size, and here's a little formula. The effective sample size is basically the sample size divided by the variance inflation factor. Some other authors also call that the design effect. So IRGT trial study designs vary. They may or may not have a baseline measurement. It is better if they do for a variety of reasons. An intervention delivered within groups could be compared to another group intervention or a wait list or other individual intervention, or some combination of these. A small proportion of these studies have more than 2 arms. And the number of and timing of the post-intervention measurements can vary. There could be a measurement right after the conclusion of the intervention, and then there could be additional measurements to determine how the intervention effect is maintained over time. So I want to talk a little bit about the history of IRGT trials. The recognition of the issues of clustering in individually randomized trials really began in the psychology literature with a paper by Martindale in 1978 that was titled "The Therapist as Fixed Effect Fallacy in Psychotherapy Research." And so this article was the first to recognize that though individuals were randomized, there could be clustering within groups or within therapists, and that had important implications for analysis. However, in public health, there was little mention of the potential for and implications of clustering in individually randomized trials until the early 2000s. At the same time, the methods literature on group randomized trials, or GRTs, was growing rapidly. There was also a mention of clustering in GRTs in the late 70s. And then in the 90s, as sample size and analysis software became available, the literature expanded rapidly. Also at that time, the computing power available made simulation studies possible, and so investigators were able to look at how different analytic methods performed, using simulation. One of the first papers in public health or medicine to detail the issues of correlation in individually randomized trials was this one by Donald Hoover in 2002. And he referred to the between group differences as heterogeneous teaching subgroup effects. He also derived the true type 1 error rate of tests that ignored correlation with varying numbers of groups and members per group, and found that that ranged from the nominal 0.05 to almost 0.5. So really discouraged the ignoring of the correlation in studies with the potential for it within groups. He presented a Satterthwaite unequal variance t-test for studies with 2 group treatment conditions, and the difference between this and the standard methods that had been used for group randomized trials was just allowing that variance to differ across study arms or treatment conditions. He also presented sample size formulas and an example for this approach, so that was helpful. And then at the very end of the article, he acknowledged that this approach couldn't really take into account covariates, and so he recommended mixed models to adjust for covariates. So the next article to appear dealt with just that approach, a mixed models approach. That was a Roberts article in 2005. So they introduced the use of mixed models to account for clustering and presented formula for different allocations of participants to study arms based on different variances across arms. So the idea there was to have optimal power, you want to allocate participants evenly across arms. But when you have different variances across arms, different correlations within groups, that can reduce the effective sample size in conditions differently. So they presented a formula to deal with that, and I'll talk about that a little more later on. They also examined the performance of a mixed model that allowed variance to differ across arms and found that it performed well. And lastly, they dealt with an issue that has been coming up in group randomized trials for a long time, the idea that you can test the ICC for statistical significance and say if the ICC isn't significant, then you don't have to take the correlation into account in the analysis. And they argued against this for a couple of reasons, and one is that these studies aren't really powered for the testing of that hypothesis. And the second is that these studies are designed to deliver treatment in groups, so the correlation is really part of the study design, so it should be included in the analysis. So next there were a couple of papers that dealt with what they called partially clustered data, and that was the Baldwin in 2011 and Bauer, Sturba, and Halfers in 2008. And so these studies had clustering in some conditions but not others. So they're the situations where you'd have a group-based treatment compared to a wait list or even bibliotherapy or something like that. And they recommended models that allowed for a between-group component of variance only in the conditions with group treatment. And the Baldwin paper actually has some supplemental material that presents SAS code to be able to do this, and it's a very nice example. So if you're working in SAS, you may want to look that up. They also dealt with another argument that comes up in group randomized trials a lot, the idea that you can add group as a fixed effect. So this basically amounts to creating dummy-coded indicator variables for the treatment group nested within condition and adding those to the model as a fixed effect. And the problem with that is that it actually inflates the type 1 error even worse than ignoring the group altogether. So it's really not a good approach. And they also discussed some additional situations, especially in the Bauer, Sturba, and Halfers article, such as adjusting for baseline, having outcomes with dichotomous or other distributions, and multiple treatment conditions. So they really started expanding the methods work there. And then there's finally a very recent paper with an interesting twist, the Andridge et al. Paper. Expanded the previous work to apply IRGT trials to studies where participants belong to more than one group. And so this could be a situation where participants get components of the therapy in different groups, or a situation where they get some therapy in a group and also belong to a naturally occurring group, like say a classroom within a school. So the Andridge paper talked about using SAS-proc glimics to fit models using random effects for both groups a participant belonged to. And they found out that you really have to do that to take into account the correlation that is within each group to preserve the nominal type 1 error rate. And they used Kenward-Rogers degrees of freedom, and the model yielded nominal type 1 error rate and good power. They also tested a generalized estimating equation approach, or GEE approach, and that didn't perform well, but they did have a limited number of groups in one part of the simulation, and so they didn't apply a small sample correction for these, so that might help the type 1 error rate. Okay, I'm going to move on to talk a little bit about sample size for IRGT trials. And this formula is a pretty standard one for 2 study conditions, and it solves for detectable difference, which is the smallest difference that we can detect with 80% power. So smaller is better where detectable difference is concerned. You want to be able to detect a small effect. Many behavioral interventions produce a small to moderate effect, so it's very important to be realistic in terms of this detectable difference. So this is the square root of, and the sigma squared y is the normal between person variance. So that's what you would have in a randomized clinical trial. And then these two components here next in the equation are the two variances for the two treatment conditions. Notice we have the variance inflation factor in the numerator. So 1 plus M1, that's the average group size in condition 1. And rho 1, which is the interclass correlation coefficient for condition 1. So in the denominator of this variance, we have N1, which is the sample size for condition 1. Now, pay attention here to the fact that you have the members per group in the numerator, in the M, and in the denominator, in the total sample size. So what this means is that if you add additional people to existing groups, you're not going to increase the power that much because it's present in the numerator and denominator. If you add additional groups, that will increase power more because it doesn't appear here. You don't change the M, you only change the N. Okay, so we have the same term over here for the condition 2. So this is going to allow for those rows to differ and for the M's to differ by condition. And then at the end of the formula, we have the critical values from the T distribution, T alpha, which is usually 0.05, and beta, which is usually 0.2, which corresponds to a power level of 80%, and then we square that. Okay, so I want to make a plug here for using the T distribution. A lot of these formulas use the Z distribution to avoid having to change this every time you change the number of groups or, the number of groups per condition. But using the Z distribution can really underestimate the number of groups you need. So this second formula is for an IRGT trial with only one group treatment. So that would compare a group treatment to a waitlist control, for example. So the first condition term here is the same. We have the variance inflation factor over the total sample size. But the second one, we just have 1 in the numerator. So if you multiply that out, taking the regular between person variance term, you'd multiply that out and you would have that divided by the sample size, which is just the usual variance in a randomized clinical trial. So, and one more thing about these formulas, it's fairly straightforward to algebraically manipulate these so that you can solve for power or the number of groups per condition instead of the detectable difference. It just depends on how you want to approach this. And it's also fairly straightforward to modify them for different distributions. So Alan Donner and Neil Clark have a book on cluster randomized trials that presents these formula for dichotomous variables. It would just be the usual group randomized trial formula where it pools these two terms. And I want to talk about the allocation ratio I mentioned earlier from the Roberts paper. So this is simply the square root of the ratio of variance inflation factors. So this is the variance inflation factor for condition 1, and this is the variance inflation factor for condition 2. And so you divide those and take the square root, and that tells you the proportion of participants that should go in condition 1 versus condition 2. Now again, you need to add those. If you're trying to increase this to optimize power, you need to add additional groups, not additional members. And that formula just reduces, in the case of having one treatment that's group-based and one treatment that is individually administered, this formula reduces to just the numerator. Okay, so this is a question that I get asked a lot in group randomized trials. How do I choose an ICC? You want to pick an ICC that's derived from a study as similar as possible to the study that you're planning. And that means similar in the study design, and importantly for IRGT trials, the duration of the group interaction. If your group is meeting for 6 months, you don't want to use an ICC from a group that meets for 4 sessions, because I would worry that the interclass correlation would be a lot greater for the group that met much longer. ICCs have been shown to differ by outcome variables, with the correlation much higher for attitudinal and behavioral variables than for physiologic variables. So keep that in mind. There are a couple of good papers that report a lot of ICCs for group randomized trials, so you can get some indication about the factors that affect ICCs. But what if such an estimate is not available for an IRGT trial? One thing that you can do is to look at unpublished data. So does someone else have a similar study? They might have published the results of a trial, but not the ICC. So it's possible to contact folks and ask about, can we just estimate an ICC based on your data? I used to recommend getting an estimate for a cluster randomized trial and using it for an IRGT, maybe using it as an upper bound. But I'm no longer convinced that that is necessarily the best idea, at least without a lot of caution, a lot of thinking about how the ICC arises in the cluster randomized trial. And, would that be similar for the IRGT trial, or could the ICC be larger? So it might be a place to start, but I'd think carefully about that. And here are a few of the ICCs that have been published. I'm not going to read through all of these, but I do want you to notice that they differ quite a lot. So this first one is from a 12-week PTSD intervention for veterans. And so these ICCs, 0.04 to 0.13, are not that large. And combined with groups of only 6 to 8, it would not result in a huge amount of variance inflation. But as we look at this next one, the Herzog paper, those ICCs were 0.32 and 0.4, so they're quite a bit larger. And in the Baldwin 2011 paper, they examined ICCs for psychotherapy studies and compiled a database of these. Now, a number of those are not group treatment studies, I don't think, but they still may provide some interesting examples. So Roberts and Roberts reported ICCs for a study of psychotherapy for schizophrenia, and those were also fairly large. And then this last paper that I talked about earlier, the ICC for a behavioral measure for youth was 0.06. So there may be others out there that I didn't list, but at least these will give you a start. I want to shift now to talking about the analysis of IRGT trials, and I'll start with those that compare 2 group treatments. And so for these, we can pull from the group randomized trials literature for some ideas about how to analyze. And first, I would say that a flexible classical approach is the mixed model approach. This approach can incorporate covariates, which is important, because you could have imbalance across study conditions. That's a typical thing to do at the beginning of a study, is to look at table 1 and check for balance of important prognostic indicators across conditions. So these models, if you do find imbalance, these models can incorporate covariates, and that includes a baseline measurement. And that is a good reason for a couple of reasons. It can adjust for pre-existing differences, but it also may actually reduce the ICC and improve power. And it estimates those covariance parameters and can allow those to vary across conditions. So, sometimes the covariance parameters are of interest in themselves, and so you want to be able to estimate those. Generalized estimating equations, or GEE, may be an approach that can be used in IRGT trials, and it can take the correlation into account in variance estimation, but unlike mixed models, it doesn't explicitly model the group variance. So it doesn't partition that variance into group and individuals. It just fixes the standard errors. for that additional correlation. The most important thing to know about GEE, though, is it is an asymptotically robust method. What does that mean? So that means that with a certain large sample size, GEE is robust to misspecifications of the correlation matrix. So you don't have to know exactly what that correlation looks like between your group members or over time, but if you have a large enough sample, that's okay. So how large is large enough? Studies have shown that that's about 20 groups per condition. So that's, in IRGT trials, that's 20 therapy groups or treatment groups within conditions. If you don't have that many, and the vast majority of IRGT trials do not have that many, you may need a small sample correction. There have been several of these proposed in recent years, and they're now actually incorporated into standard software, including SAS, so that's convenient. Another approach that's been used a lot in group randomized trials, particularly early on where computing power wasn't extensive, permutation tests. These are also called exact tests. And they are based on the idea that under the null hypothesis of no effect of the treatment, groups are exchangeable, meaning they could be swapped back and forth in either treatment condition, and you shouldn't see a big difference in the effect. So that would be the difference between treatment means. And so you can get a p-value by placing the observed effect in a distribution created by all possible arrangements of those group effects across conditions. And so these are really the gold standard for testing for significance. The only thing is they're inadvisable if the group sizes differ across arms. So it may be something that you can't use for a lot of IRGT trials, but if you have the same group sizes and amount of contact across conditions, then those may be a good approach. And finally, Bayesian methods may be more flexible in allowing the incorporation of prior information on the ICC and other parameters of interest. You can actually allow the random effects to have different distributions here in the Bayesian approach, which you can't do in the classical approach. And so analysis of IRGT trials that compare a group treatment to individual treatments. These are the studies that others referred to as partially clustered. And they're more complicated than studies with group treatments in both arms or both conditions. So you can use the Satterthwaite t-test approach and compute variance for each condition separately. And then just construct a t-test dividing the difference between means by the variance, allowing those variances to differ across conditions. You can fit mixed models that allow the correlation structure to vary across arms. And this is where you take the Baldwin approach and model correlation in arms with group treatment only. So you only fit a group component of variance in one arm. And then again, the Bayesian methods that allow incorporation of prior information about covariance parameters. I want to make a comment about degrees of freedom because when you use mixed models, you have to select a degree of freedom method. And the default methods often don't deal with complicated models very well. And so degrees of freedom should be based on the number of independent units in the analysis. So this is easy for group randomized trials and randomized clinical trials. The groups are the independent units in a group randomized trial and individuals in a randomized clinical trial. But in IRGT trials, it's less clear. So the Hoover paper reported a Satterthwaite method. Baldwin examined Satterthwaite and Kenward-Rogers method and found little difference. And the Andridge paper recommended Kenward-Rogers degrees of freedom. So both of those methods take into account the correlation in determining the number of independent units, and both have performed well in multiple simulations. Oh, I should say about degrees of freedom. If you're using SAS, do not use the between within methods because those, for degrees of freedom, because those don't perform well. And so I want to talk about reporting requirements for IRGT trials because, as you'll see later on when I present the results of reviews of these studies, very often important aspects of the trial are neglected in reporting. So there was an extension of the consort statement a few years ago to non-pharmacologic interventions. And so this wasn't specific to IRGT trials, and it's possible that a statement is needed for IRGT trials, but it did point out a number of important things that are needed in reports of these studies. So for each study condition, you want to talk about whether treatment was administered in groups or not, and fully describe the intervention that was given. You want to report the number of groups and members per group. Report the sample size calculations in detail, including the ICC that was used or the variance inflation factor. And then also report the ICCs for all trial outcome variables and by study condition if applicable. So if those varied by study condition, you want to report them for both study conditions. So that means you're reporting two ICCs, the one used in sample size calculation and the one that actually resulted from the data. And then describe in detail all analytic methods used, including degrees of freedom. Okay, so David mentioned the 2008 review that we did. We've reviewed all published IRGT trials that appeared in 6 journals, and we have the journals listed here. And so most of them were in preventive medicine, health psychology, obesity, addictive behaviors, and just a couple in AIDS and behavior and American Journal of Public Health. The vast majority of these had 2 study conditions, but 8 and 3 had 3 and 4 study conditions. And when you think about the impact of power, the impact of the intraclass correlation coefficient on power, you have to wonder if these studies had sufficient power to have that many study conditions. The number of group treatment conditions, most studies had 1 or 2 group treatment conditions. A few had 3 or 4. And so then the baseline sample sizes, the majority were less than 200 participants, many of them less than 100 participants, and so that raises questions about power, again, whether they were adequately powered. So these are, it says review methods, but this is actually the results. 32 of the 34 articles reported analysis at the individual level, ignoring the group entirely. So this means they made no mention of the group at all, conveyed no awareness that delivering an intervention in groups could mean correlation within groups. 2 reported mixed model analyses and 1 reported structural equation modeling. And we determined by review of 3 of the authors for each paper that only 1 article reported appropriate analyses. 32 reported inappropriate analysis, and 1 didn't have enough information to judge the analytic methods. And so that gets back to the reporting requirements I just went over. You need to have enough detail on the analytic methods for the reader to judge. Then we reviewed, in 2011, HIV/AIDS-focused group randomized trials and IRGT trials published in 7 journals, and I'm only going to talk about the IRGT part of the review here. We identified 25 IRGT trials, and none of the 25 reported sample size calculations taking intraclass correlation into account. 2 reported appropriate analytic methods, and 21 reported at least 1 significant trial outcome. So what that means is that many of those significant trial outcomes could have been from studies that used inappropriate analytic methods and had a much higher type 1 error rate than the nominal. I also want to mention this paper, the Baldwin, Murray, and Shadish paper. This was a really great paper that looked at 33 group psychotherapy treatments. They're designated as empirically supported treatments by the American Psychological Association. So these treatments have been disseminated widely. Of the 33, they found none appropriately analyzed their trial data. And when they applied a post hoc correction to look at how many would be significant when they corrected for the correlation, they found that between 6 and 19 of the treatments would no longer be significant if appropriate methods were used. But they did highlight the fact that they were using ICCs from papers that may report on studies very different from the ones in this compendium. So they recommended compiling a database of ICCs so that corrections to prior studies could be made with better precision, and also so that investigators would have these ICCs when planning future studies. So to present some conclusions, although work on group randomized trials has been plentiful and recognition of the impact of correlation has increased, the same can't be said for IRGT trials. We really only have a handful of methods articles at this point, and virtually no recognition of these issues in published trials. And the methods work has been clear that ignoring the ICC and in some cases different group sizes and differing variance across conditions can inflate the type 1 error rate, sometimes substantially. And sample size and analytic methods are now available for a variety of study designs, and article reviewers and journal editors really should require appropriate methods for these trials. I want to highlight some future work that I said earlier was desperately needed for IRGT trials. One thing is an ICC database for public health outcomes. We need data from IRGT trials with a variety of study designs, intervention durations, outcome variables, etc. And really, since any one study has limited power and a limited number of groups, sampling error for these ICC estimates is going to be large. So really only when we get a few studies for an ICC can we have some confidence that in the value of that ICC. So we also need to determine the impact of covariates on IRGT trial ICCs. This is work that's been done for group randomized trials, and we have a pretty good idea in some areas of what covariates will reduce ICCs and by how much. And so we need the same for IRGTs. We need sample size estimation software. Not everybody is able to take the formulas that I presented and do the algebraic manipulation and come up with the exact sample size estimation formula that they need and employ that properly. So we need to have packaged software that enables people to do that. We need further reviews to demonstrate whether awareness and use of the proper design and analytic methods improves. So far, we see very poor recognition of this issue. So, and we also need further reanalysis of IRGT trial data that was originally analyzed improperly. Now, this isn't always possible. I've tried a couple of data sets that I've gotten here, and unfortunately, the group indicator variable for which group a participant received treatment in isn't always in the data set. So hopefully, we will correct that going forward. Okay, so last I'm going to ask for questions and offers of IRGT trial data or ICCs. If you have such trial data, you can either send me the data and I can do the analysis and we can work together for publishing that, or I can guide you. If you can't release the data, I can guide you through estimating the ICCs, and that's been done before, was done in the Baldwin paper. So reach out to me and let me know what you have. And I'm going to stop there and ask for questions.
Thanks, Sherry, very much. Terrific presentation, very clear. I'm going to ask one clarification question, and then I've got a whole just slew of substantive questions. The clarification question, you might want to go back to your slide 11 or slide 12, if that's possible. to put your formulas up. Sorry?
That's all right. Yes.
So, yeah, here we go, 11. So the N, there you've got an N1 and an N2, and you say that's the sample sizes for conditions 1 and 2. Is that the number of groups, small groups where the intervention's being delivered in each of those 2 study conditions, or is that the total number of people in each of those 2 study conditions? Can you clarify?
That's the total number of people, and I know you use MG there to be clear. So it's the number of members per group times the number of groups.
Okay, but your intention is it is the total number of people.
It's the total sum. Yeah, this is how it was presented in the Baldwin paper. And so since I was referring people to that paper so much, I wanted to be consistent. But I agree that it is a little confusing if you're used to notation that breaks those out separately. All
right, thanks for clarifying. So some more general questions. Somebody has asked, how do I know if the ICC or variance inflation factor is small enough to ignore?
So that's a question that comes up in group randomized trials a lot, and I've actually seen people report in papers the ICC was only 0.01, so we did not fit a mixed model or take into account the correlation. The problem is, when I presented that variance inflation factor, and you can see it here on this slide, that ICC is multiplied by the number of members per group again. So, you know, even a small ICC, you know, an ICC like 0.05 with 30 members per group can result in nearly a 50% increase in the variance inflation. So, or in the variance relative to independent observations. So I really would say that I wouldn't ignore any ICC. It's part of the design, and I would incorporate that ICC just as a plan from the very beginning.
Since a positive intraclass correlation reduces power, and we can see that in the formula because it makes the detectable difference larger, and we want usually a small one. What can you do to increase power in an individually randomized group treatment trial?
So there's a couple of things, and one is something I pointed to a couple of times, and that's to include covariates to reduce the ICC. And what we want to do there is to think about what leads people to respond similarly within groups. And is it anything that we can statistically adjust for? Are there more women than men in a group, and is that related to the outcome? Age, other demographic factors. But the most important thing is adjusting for a baseline measurement. So that's been shown in group randomized trials to reduce the ICC more than anything else. And so including that baseline measurement reduces or removes that variability that was existing before the intervention. So that's a really great way to improve power. And of course, you increase the degrees of freedom by having another measurement too. So then the other thing is, and people laugh at me here when I say this, but make the intervention more impactful. So think about, is there any way we can make this intervention more powerful? Can we increase the length of time? Can we include other components that other people have found to be successful at improving whatever our outcome is? And finally, including more measurements. In addition to a baseline measurement, maybe think about including more post-intervention outcomes. I don't know, have I left anything out?
Sounds good to me.
Okay.
We have questions about are there websites or software packages that will help someone do sample size calculations for an individually randomized group treatment trial?
So there's one that I like if you're working in Stata. I forgot to say that I have a couple of reference slides here, and some of these papers have good examples of, the Baldwin paper, 2011, has good examples of SAS code, and he goes through each of the options for, you know, things that you can include in the model and how you can fit more than one or more than two treatment conditions and things like that. Chris Roberts, who wrote the 2005 paper, has a page that's got a lot of helpful resources on it, but one of them is a sample size calculation procedure called CL-SampSci. So it's easy to download and install that, and his page has instructions on how to use that. And then there's also the NIH page, which I assume you guys go over at the end of here, but here's also the link. It has resources on group randomized trials, including a sample size calculator, and I believe, if I'm not letting the cat out of the bag early, that you all are developing an IRGT trial sample size calculator?
That's the plan. It's not there yet.
Okay. Yeah, so, and then if you have the capability of doing simulation studies, you might get to the point, if you have multiple measurements and an outcome with a less standard distribution, you might need to do simulation studies to look at power. And that's where, if you don't know how to do those yourself, it's a good idea to consult with a statistician.
Full employment for biostatisticians.
Yes.
Other questions here. Is the design effect the same thing as the effective sample size?
No, the design effect is, the effective sample size is a function of the design effect. So you would take the sample size, the raw sample size, and divide it by the variance inflation factor to get the effective sample size. And that's sort of a crude way that you can do sample size calculations, by dividing and getting the effective sample size and then putting them into a naive power calculator that ignores the clustering. So I do that sometimes when I want a really rough estimate and, need it quick.
Yeah, that doesn't take the degrees of freedom into account, does it?
No, it doesn't. It doesn't. It works better if you have large studies. But yeah, that's and Alan Donner in his book uses the Z distribution and then rounds up. And it's a great book, but that particular thing, I don't love that, because in really small studies, you can underestimate the number of groups needed.
If you're going to estimate an intraclass correlation from preliminary data that you have, or you're reaching out to another investigator who's done a study something like yours and has data and is willing to analyze it, do you get an estimate of a crude intraclass correlation, unadjusted in other words, or do you try to get an intraclass correlation estimate from a model that includes covariates? Which one of those is preferable?
I would do both. So in fact, I do a series of them, and I've published a couple of papers for group randomized trials, ICCs, doing this, presenting the crude ICC and then one adjusting for a very limited set of demographic covariates, and then one adjusted for expanded covariates. And that's so that you can get an idea of how the covariates help in reducing that ICC, and for me to be able to present ICCs in a paper and give people a range of ICCs to choose from.
If you're going to include the baseline measurement in your analytic model, so let's say you have a pre-test, post-test design, and you've got baseline data. You've recommended adjusting for it because it can reduce the intraclass correlation. Are you talking about including it as a covariate, or are you talking about including that pre-test and post-test as two levels of time in a repeated measures mixed model?
So in the group randomized trials literature, there are a couple of papers that show that most of the time including it as a covariate is the most powerful approach, and that's actually true of randomized clinical trials as well. So I would recommend that, but it's a good idea to see those papers, and Dr. Murray's a co-author on those papers, so they're easy to look up. And consider your specific situation. It's helpful if you have parameters like the correlation over time for your outcome variable, and obviously numbers of groups and members, and that will help you consider which approach is likely to be more powerful.
What if part of the effect of the treatment that you're delivering, the intervention that you're delivering, is to increase the similarity in responses of the participants? In other words, it creates correlation within the small group. It effectively creates or increases the interclass correlation. Aren't the analytic methods that you're talking about going to get rid of that and effectively get rid of some of your treatment effect?
You know, this is a question that we got years ago, I think, when I presented this at a conference. And I think your goal may be to promote interaction among the members of a group in order to improve their outcomes, but I doubt that your goal would be to increase between group variation, because that would mean that some groups do better than others. So I don't think that would be the goal. And even if that group interaction is the goal, it doesn't get around the statistical issue that you have to take that interclass correlation into account in having appropriate variance.
So if you were to leave that, if you were to ignore that correlation because that's part of the result of your intervention, you'd be reporting a p-value that's inappropriate, or
yes, absolutely. I think at this point we have 3 decades of research on that, and if you're a statistician, all you have to do is derive the variance of those condition means, and you can easily see that you'd be inflating the type 1 error rate if you ignored it.
Yeah, we have a question, a completely different kind of question. How do you recruit schools or work sites or communities or other such groups to participate in a study that's going to be a group randomized trial or an individually randomized group treatment trial?
Oh, wow. Okay. That is not my specialty, but I've been involved in some of it as studies have gone on. And I think the key is making contact with that school administrator or the group leader. In my case, it's very often in villages in Africa, and it involves getting buy-in from the community leaders, like tribal leaders and such. And so it's really sitting down and communicating how important the study is and what it's going to do for the population that you're targeting. And further than that, you probably have to ask a behavioral scientist.
Yeah, I think that's a really good answer, though. In a traditional randomized clinical trial where we're randomizing individuals, the pitch or the recruitment effort is aimed at the individual, and it's their decision whether to participate or not. When you're expecting to randomize groups in a group randomized trial, then you really need to talk to the leadership of the groups and persuade them that it's an important scientific question and it's worthwhile. In an IRGT, since you're randomizing individuals, isn't the pitch or the recruitment still going to be aimed at those individuals, even if they end up getting some of their treatment in small groups?
Yeah, I think so. So you're still trying to enroll individuals and doing the same thing that you would do in a randomized clinical trial. One thing I realized I forgot to mention, and it has nothing to do with this question, but when I was talking about reducing ICCs, there's some indication that manualizing treatments, spelling very clearly out in a manual how the treatment is to be administered, and ensuring fidelity to that treatment manual can reduce ICCs. But then again, that's not for every situation, because some treatments involve really adapting to the participants you have. So that's not applicable in every situation. I just wanted to put that out there.
So you've offered an invitation to members of the audience to share data with you or collaborate with you on papers. Can you go back to the slide that shows how people can get in touch with you and say a little bit about what sort of information they would need to send you if they want to pursue this invitation?
Okay, so I would need to know the detailed information about the study. So if there's a study protocol or a publication that describes the study, the intervention, and those details, I would need that. And then I would also need data that, most importantly, has an indicator for the group a participant belonged to, and then covariates of interest, and we can talk about what those might be. I think a first step might be reviewing the protocol or study description and then talking with the investigator about what covariates might influence the outcome and also what covariates are in the data set. And then we could come up with a reduced data set from the entire trial data set. Or like I said, I can guide the investigator through doing this analysis. And that can be done in SAS, Data, R. I'm not completely sure about SPSS's capabilities, but there's definitely a mixed model procedure. I'm just not sure it allows the variance to vary across arms.
One of the things that you mentioned in that list of pieces of information that you would need was an indicator variable to identify the small group that a person received their treatment in. You cited the Andridge paper, which talked about people being in more than one group, and we also could imagine the situation where people change groups. So maybe they go to the Tuesday evening session to get their weight loss treatment for a while, and then their schedule changes and they have to go to the Thursday evening session. Is it important to keep track of all of the different groups that a person is in where they receive treatment, and do you need to take all of that into account? It could get rather complicated.
Yeah, absolutely. I would say keep track of it, and we can deal with the analytic complexity in a variety of ways and see. Now, you definitely, the Andridge paper pointed out that you definitely do have to take into account multiple groups that a participant belongs to, but what we don't know is how large are those ICCs. If a participant belongs to a classroom and then goes and gets one session of a group treatment, how big is that ICC? How big is the variance inflation factor? And those are the things that we don't know. We have enough methods work now to say we have to take it into account, but how big are those ICCs? That's a pretty big mystery.
Okay. Terrific discussion and lots of great questions from the audience. I appreciate it very much. And Sherry, I want to thank you for a great presentation. I'm going to turn this back over to Marie, and we're going to close off the session as we hit the 1 hour mark.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. On the MindTheGap website, prevention.nih.gov/MindTheGap, you'll find several resources for this talk, including the slides and a list of references. We'll also be posting a recording of today's webinar on our website next week. You'll receive an email with a link to the recording when it's available. Thank you.